Okay guys, welcome to today's video. Today we are doing proof by mathematical induction. And here's an example of a question that we might get. Prove by mathematical induction that 3 to the power of n minus 2n minus 1 is divisible by 4 for all integers greater than or equal to 2. Now, for all of our proof by induction, we're going to follow the same process. So we want to remember these 3 steps. Okay, our first step is to show, and what we're going to show is that our proposition works for the first value of n that we can do, or the lowest value. So let's run through with this example. Our proposition is 3 to the power of n minus 2 n minus 1, and we want to show that this is divisible by 4. The lowest n that we can choose is 2, so that's what we're going to start with. We're going to show that n equals 2 is hopefully divisible by 4. So let's find P2. 3 to the power of 2 minus 2 times 2 minus 1 is 4. Now, I like to do this. I like to say that that is 4 times 1. I know it's a little bit obvious, but very clearly now that is divisible by 4. Second step for our proof by mathematical induction is assume. We're going to assume that our proposition works for n equals k. So for this example, we want to assume that our proposition holds for n equals k. So let's write our p of n. This is our proposition, 3 to the n minus 2 n minus 1. So we are going to assume that pk is 3 to the k minus 2k minus 1. And if we're saying that that's going to be divisible by 4, then that will be 4m, where m is an integer. And our third and final step is to prove, and we're going to prove that our proposition holds for n equals k plus 1. And in all 3 of these things, it proves our proposition works for all the values of n. Okay, and the last part of our proof here is the actual proving bit. So I want to prove that this works for n equals k plus 1. Now, if I combine all those 3 things that we've done, which is show, assume, and then prove, then all that together will prove by mathematical induction. So let's get into it. So p of k plus 1 will be 3 to the k plus 1 minus 2 to the k plus, or times k plus 1 minus 1. Now the trick with these ones is what we are looking for is this. And then I'm going to substitute my 4m. And I know that m is an integer. So 3 to the power of k plus 1 I can write as 3 times 3k minus 2k minus 2 minus 1. Now this has got a multiple of 3. So if I go 3 times 3k, can't really change that. But this one I want a minus 6k, which means I'm subtracting an extra 4k, which means I need to add 4k. Now that groups together to minus 3, which is nice because that is my multiple, but I also need to plus a 4k on the end here. So now it is the same. All right, now I can take out that factor of 3. Plus 4k. And then now I can make this substitution because this here I said was 4m. So this becomes 12m plus 4k. I'm running out of room, so let's just write, I'm going to get rid of this. Let's write it up here. 12m plus 4k. 12m plus 4k. And then I can take out that factor of 4. So that's 3m plus k. And I assume, so therefore, divisible by 4 because m and k are integers. So that number must be divisible by 4. And therefore proven by mathematical induction. So every single mathematical induction question is going to be the same. We're going to follow those 3 steps. That is 1, show, 2, assume, 3, prove. We also have 3 different types of induction questions. The first one is division, which is the example that we just did. The second one is summation, and the third one is inequality. Now, over the last 10 years, we've had 4 division questions and 5 summation questions, only 1 inequality. But we'll do an example of a summation and inequality now. Okay, so let's start with our summation example. Prove by mathematical induction for all integers greater than or equal to 2, and we have our summation there. So let's start with our show and pick our lowest value of n that we can. So in this case, 2. So in my left hand side will be 2 times 1, which is 2. My right hand side is 2 squared minus 1 all over 3, which is 2 times 3 over 3, which is 2. So left hand side equals right hand side. Okay, done. So after we show, we assume, and our assumption is n equals k. So 2 times 1 plus 3 times 2 plus all the way up to, so n, but n is k, so k minus 1, and that is the same as k squared minus 1 all over 3. Alright, so this is important for our next step. This is just our assumption, so then we need to prove n equals k plus 1. We need to prove that this works. Alright, so the way I like to write these, I'm going to write basically the same thing. I'm even going to include this term, but of course there's going to be the k plus 1. So it's k plus 1, and then k plus 1 minus 1 will just be k, and then this will be k plus 1, k squared, whoops, sorry, that'll be k plus 1 squared minus 1 all over 3. And I'm going to use my assumption that we made, this assumption, I'm going to use that here, because I said that this is of course equal to that, and I have that in here, so hopefully you can see that. That's why I wrote it out like this. Okay, so we can say that my left hand side will become k squared minus 1 all over 3 plus k plus 1 k. Now if we're going to group everything together here, we can get k cubed minus k plus, now I need that common denominator is going to be 3, so there's going to be 3k squared plus 3k, which, grouping my like terms, that's k cubed plus 3k squared plus 2k over 3. I can take out a common factor of k, run out of room, sorry, so that'll be k squared plus 3k plus 2 all over 3, and I can simplify that to k plus 1, k plus 2 all over 3. Now run out of room, but we should hopefully be able to show that our right hand side equals that. So let's clear that. So remember my right hand side was k plus 1 squared minus 1 all over 3. So that is k plus 1. Now that would go to k squared plus 2k plus 1 minus 1 if I just expand that perfect square. Of course the ones cancel there, and there's a factor of k in those terms. So I can go k plus 1 and k plus 2 all over 3, which is my left hand side. So we did it. So therefore proven by mathematical induction. Okay, last example for today. Prove by mathematical induction that for the integers n is greater than or equal to 6, that n factorial is greater than e to the power of n. Okay, so where do we start? Of course we start with show. pick our smallest value of n that we can. So in this case 6. So 6 factorial, that is my left hand side. Left hand side is 6 factorial, which is 720. And my right hand side will be e to the power of n, which is 6. And that is 403.428 ... So clearly my left hand side is greater than my right hand side. Okay, so once we've done that, then of course we assume, and we assume n equals k, we assume that our proposition holds, so we assume that k factorial is greater than e to the power of k. And after we've assumed, we need to prove that it works for k plus 1. So k plus 1 factorial is greater than e to the k plus 1. Well, factorial, of course, I could write my left hand side. I could write my left hand side as k plus 1 times k factorial. And I could write my right hand side as e times e to the k. Okay, so hopefully clearly you can see why in fact my left hand side would be greater than my right hand side, because I've already proven that, or I've assumed that k factorial is greater than e to the k, and k plus 1 is also greater than e, because of course k has to be bigger than 6. So k plus 1 has to be bigger than e, because e is only 2.71 ... So therefore proven by mathematical induction. And that has been proved by mathematical induction. Next video I'll do some past HSC questions, so I will link that in the description. Just always remember those 3 steps: show, assume, prove. Smash the like button, hit the subscribe, and I'll see you in the next video.